Well, good morning there, Advanced Chemistry, and I hope you had a wonderful day away from school yesterday. This morning I want to review with you some things that we learned towards the end of last year when we were discussing covalent bonding. Remember, covalent bonds are made when atoms will share electrons. We were discussing during that time of covalent bonding these things called Lewis structures. And Lewis structures show us how an atom's bonds are arranged within a molecule. Excuse me, I got to get my tools here up. So Lewis structure is designed to show us what the atom looks like, so where those bonds are, and then the overall shape of the molecule, which is going to help us identify that molecule as being polar or nonpolar overall. So I wanted to do a couple of examples with you to get you started, to jog your memory, so to speak, and then give you the opportunity to practice today. So here we go. We're going to start with sulfur dioxide, this SO2. And SO2, first we want to make sure that it is indeed a covalent bond that's going to be present between the S's and the O's. And we do that by looking at the differences in electronegativity between those two atoms. So you're going to need your periodic table in order to find those electronegativity values. And for sulfur, that value is 2.58. And oxygen is a 3.44. So that difference there falls within the range on your difference in electronegativity chart there. It falls between the 0.5 and the 1.6 values, which shows that this is going to be a polar covalent bond between the S's and the O's. So oxygen has a higher electronegativity, meaning it's actually pulling the electrons significantly closer to itself away from the sulfur. And we'll talk about that more in a second, but it is indeed covalent. Covalent would be a difference anything below 1.7, so like 1.6 and below. And because it's in that range of 0.5 to 1.6, we're going to call it polar covalent, just indicating that those electrons are shared, that's the covalent piece, but not shared equally. That's the bond itself. This portion right here where we identify as polar or nonpolar goes for the overall molecule, which we need to know a little bit more information before we can decide that. So let's draw the Lewis structure. And if you will recall, what we need to do for our Lewis structure is first to determine how many valence electrons we have to work with. So last year, if you had me anyways, we called these the halves. So how many electrons do I have to work with? And we only count valence electrons because they are the only ones that actually participate in making bonds. So when electrons are shared, it's only the valence electrons that are shared. So in this molecule, my sulfur, there's one sulfur atom, and that sulfur has 6 valence electrons, and that comes from where it is in the periodic table, its electron configuration. It's in that family number 16, and that gives it 6 valence electrons. There are 2 oxygen atoms. It's in the same family, so it's also going to have 6 valence electrons. That means we have overall 3 times 6, 18 valence electrons with which to work. And we need to make everyone feel happy or stable with those 18 valence electrons. Well, if next I do my wants, in order to be stable, each one of these atoms is going to want a certain number of electrons. Now, for most atoms, that number is 8. So sulfur wants 8, and each of those oxygens want 8. So overall, that's a total of 24 valence electrons that we would need to separately make everyone feel happy. So because those numbers don't match, I only have 18, that means I'm going to need to do some sharing, and it's going to require a sharing of 6 valence electrons or 3 shared pairs of electrons, because electrons can only be shared in pairs. So this is our important value right here. You can ignore letter B here for a second. Generally speaking, and if you remember our values for electronegativity were 2.58 and 3.44, the least electronegative atom is going to be placed as what's known as the central atom. And the central atom is important for drawing the Lewis structure and then for identifying the shape of the molecule using the Vesper theory, which we'll need to do here in a second. But we'll start with S as our central atom because it is lower in electronegativity. And then the O's can just kind of go around the S. It doesn't really matter where. And then to be connected to each other, and if you think your central atom is kind of the middle of a wheel, and all the other atoms have to kind of go on the spokes, or the outside of the wheel, there need to be 3 shared pairs between the central atom and the outside atoms. So I'm going to draw on those shared pairs. There's one shared pair. That's going to connect the oxygen and the sulfur to each other in the molecule. And there's a second shared pair connecting the sulfur to this oxygen in the molecule. As we go through sharing our pairs, we want to see if anybody is happy or feeling stable because of our sharing. And right now, this oxygen here has only 2 valence electrons, so it's not stable, as does this one. The sulfur has 4, so it is also not stable. But I also haven't shared all my pairs. I have 3 to share, and that third pair can either go here or here. It doesn't matter which. I'm going to go ahead and put it there. So that is all the pairs I can share. So I'm done sharing now. Everything else can't be shared. It has to be a lone pair. So I'm going to go through and make everyone else stable by having 8 valence electrons. So this oxygen currently thinks it has 4 valence electrons. So I'm going to add on 5, 6, 7, 8. So 2 lone pairs. And that oxygen will then be stable with 8. Sulfur right now has 2, 4, 6 valence electrons. So I'm going to put the 7th and 8th as a lone pair. We could have put those on the bottom too if we wanted to. And now sulfur is stable. These 2 shared pairs represent a double bond, a double covalent bond. And then this oxygen would then need 3 lone pairs, giving it a total of 8. So on this side we have a single covalent bond. So in our Lewis structure, the last thing we want to do is make sure that we have not exceeded or gone below the number of valence electrons that we said we actually have in the molecule. So we have 18. So we'll back through and count up valence electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18. So that gives us our 18 valence electrons, which is what we said we had. So that means we've done the structure correctly. We can then go and write the structural formula for this, but while we do that, let's go ahead and do the shape at the same time. So we're going to replace our bonds here with dashes to indicate bonding, but we're going to want to go to your VSEPR chart, and I'll show you that here in a second, and find what happens when around my central atom I have 3 shared pairs. So around this central atom we've got 1, 2, 3 shared pairs, 1 lone pair, and the number of atoms that are attached to that central atom. So I have 2 attached atoms, because that's going to tell me my shape. So this is unimportant for you to write down. I'm just writing it down so we know where to look on your VSEPR chart. So I made some copies of those VSEPR charts for you to look at if you happen to have lost yours from last year. So you can get one of those. And we're going to look on our chart, get rid of this. We're going to look on our chart, should look like that, and we're going to find on this chart where we have 3 shared pairs. Well, there's 3 shared pairs, 1 lone pair, but this is 3 attached atoms. We only have 2. So it's right here, 3, 1, 2. So that tells us we're going to have a bent shape. So I'm going to go back to this slide, redraw this sulfur dioxide. So that means a bent shape. There's my lone pair. Here's my double bond. And this comes from that Lewis structure. I'm just replacing where it overlapped with a bond. Keep the lone pairs. There's a single bond here. And there were 3 lone pairs around that oxygen. And now we have the proper shape of that molecule as well. And a bend is sort of like a boomerang. So in this molecule, the reason that it's bent is because these lone pairs and these bonding pairs are all electrons, and they're all negative. So they kind of push away from each other as far as they can get. So if you picture like these electrons are kind of occupying a space over here 3-dimensionally, and then these bondings, and they're all sort of pushing each other away. So we end up not with a straight across linear, but those are pushing as far away from each other, including the lone pairs, which we just don't see in the molecule. So the molecule itself is this bent shape, but it's because of the existence of this lone pair. So the last thing we want to do on our Lewis structure is to identify whether or not the molecule is polar or nonpolar. And we do that by drawing some arrows. So back to our original electronegativity values here, we said that because those have a difference between 0.5 and 1.6, it is a polar covalent bond, meaning the electrons are going to move significantly enough to show that they are being pulled towards the oxygen. And since this bond is really identical in terms of electronegativity, it's going to happen that way as well. Well, when this happens, remember overall, now this oxygen sort of has the electrons more often than the sulfur. So the sulfur is getting a sort of positive charge or deficit as the electrons move towards the oxygen. So the oxygen has a partial negative charge and the sulfur has a sort of positive or a partial positive charge, which we show by this little squiggly. And then the final question, when we identify this as polar or nonpolar, is looking at this, we have to decide if there is an overall movement of electrons in this molecule. Would there be a large arrow that we could draw that shows the overall movement of electrons? And the answer is yes. The overall movement of electrons in this molecule is down. So we can draw a big arrow showing that overall the electrons are moving down towards the bottom of this molecule, at least the way that we have it drawn. So that's a quick review. I do want to add one piece to this, which is going to help with our upcoming unit, and that's to show you what's known as the formal charge of all the ions in the compound. So I'm going to redraw this compound to clean it up a little bit to show you how to do that. The formal charge of a molecule is actually finding the formal charge of each atom in the molecule, and it's kind of a way of bookkeeping the electrons that each atom has within the molecule, or the number of electrons that atom feels like it has in the molecule. So what we do is we take each bond, oops, I forgot my lone pair there, and we split each bond in half, and we pretend like each atom on either side of the bond is getting exactly half the number of electrons from that bond. So if I were to count the number of electrons in this oxygen atom over here, I would count 1, 2, 3, 4 for the lone pairs, and then this bond is 2 shared pairs or 4 total. So we would have, and if you want to visualize that, it would kind of be like dot, 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 dot. So we'd be getting half of those 4 electrons. Draw that back up there. So when we take this bond and we divide it in half, that's 4 electrons. So we're going to have 5, 6. So this oxygen has 6 electrons. Now we want to compare that to what we normally have. And oxygen has normally 6 valence electrons. I'm going to use yellow. So since that's the same, this oxygen has a formal charge of 0. So 6 here in the molecule, we compare that to 6 that it would normally have, so the formal charge is 0. Now we're also going to do that for the sulfur right here. So let's go ahead and do that. For the sulfur, sulfur is going to get the other 2 in this bond. So we've got 1, 2, 3, 4, and then this is only a single bond, so that's 2 electrons. So sulfur is only going to get just one of those 2. So sulfur is going to have 5. And if you look at the periodic table, sulfur normally has 6. So we are 1 electron short. So when I'm 1 electron short, the formal charge on sulfur is going to be +1. Now when we know the formal charge, we go ahead and write it right on top of that atom. So oxygen is 0, sulfur's formal charge is +1. Let's do the same thing for this oxygen over here. So oxygen gets 1 of the electrons from this bond, 2, 3, 4, 5, 6, and 7. So this oxygen has 7 valence electrons in the compound, and normally on the periodic table oxygen has 6. Now that means I have 1 more electron than normal, which gives me a -1 charge. So that is just an idea of how electrons are distributed throughout the molecule. And what's neat about this formal charge is that the overall charge of the molecule should be the same as the sum of our formal charges. So if we look at our formal charges, I have 0, plus 1, minus 1, so my overall charge is 0, so this molecule should be neutral, and it is. So we're going to continue to practice that. I'm going to go through one more example with you, and that is the cyanide ion right here. So I want us to go ahead and do the Lewis structure, the shape, polar or nonpolar, and then formal charge. So we'll start with our Lewis structure, but before we do that, just a quick double check. Carbon's electronegativity is 2.55, and nitrogen's electronegativity is 3.04. Now that is a difference of 0.49. If I round up, that is a difference of 0.5 to the nearest tenth, which means that this is going to be a polar covalent bond. For my halves and my wants, let's do that to get us a molecule. Halves. Carbon, there is one atom of carbon with 4 valence electrons, and there is one atom of nitrogen with 5 valence electrons. Since we have a -1 charge, we're going to have an additional electron than we would normally. That's where the -1 charge comes from. So we're going to add that to what we actually have in our molecule, in this case a polyatomic ion, which means we're going to have 4 plus 5 plus 1, 10 valence electrons. Now for our wants, each one of those atoms still wants 8 valence electrons. The existence of one additional electron has not changed that. So we still want 16 valence electrons. That means with our 10 electrons, we're going to have to share 6 of those electrons, or 3 pairs. So we're going to have 3 shared pairs just like last time. Now normally we would pick a central atom, but since we only have 2, there really doesn't need to be a central atom. There's just a C and an N, and all of our shared pairs are going to go between them. So that's 3. I'm going to go ahead and add them in. 1, 2, and 3. That means carbon right now feels as though it has 2, 4, 6 electrons. We're going to add the 7th and 8th in the form of a lone pair. We're going to do the same thing on nitrogen, but first we're going to circle those 8 for carbon, and then we're going to have 3 shared pairs or a triple bond in between them. Now for a polyatomic ion or a radical, something that has an additional or a deficit of an electron that it would normally have, we put that in brackets and put the charge on the outside. Now let's take a look at the shape here. What we have is a central atom with only one atom attached. So we don't even really need to look at our VSEPR chart. If these electrons are getting as far away from these electrons as possible, that should be 180 degrees or a straight line. So this is linear. So when I draw this molecule, I'm going to draw a straight line like so. Because it is linear and because it is polar covalent, back to our first part, and because carbon is less electronegative than nitrogen, it is going to be a polar molecule with the partial negative end being on the nitrogen side and the partial positive end being on the carbon side, with an overall -1 charge. So it is polar. The bond is polar, which makes the molecule polar. Finally, let's do your formal charge, and I'm going to erase all this, draw it a little bit bigger. If I have this molecule, in this case, a charged molecule, and I want to do the formal charge, what I need to do is split this bond in half and count. So carbon has 1, 2, and then half of these electrons. So 3, 4, 5, because there are 6 involved in a triple bond, so carbon gets 3 of those. So carbon has 5. According to the periodic table, carbon would normally have 4. So that means carbon has a formal charge of -1. It has an extra electron. So formal charge of -1 for the carbon. So we write that right above it. For the nitrogen, nitrogen gets the other half of those bonds, 1, 2, 3, 4, and 5. So nitrogen also has 5, and according to the periodic table, nitrogen usually has 5. which is a formal charge of 0. Remember what I said about the sum of formal charges, -1 and 0 will give me an overall charge of -1, and of course we know that Cn minus 1 has an overall charge of -1. So that does hold true here. So we've got a formal charge of 0 on our nitrogen and -1 on our carbon, giving us an overall charge of -1. So what I'd like for you to do next is I'm going to put 3 on the screen. I'm going to ask for your substitute to pause the video here and have you try those 3 on your own. Try the Lewis structure, the shape, polar or nonpolar, and then formal charges for those 3. So that should take you a little bit of time, and then we'll go through the answers. So here are the ones that I would like for you to do those for, and then I will put the answers on the screen. So we've got HSO3 -1, that's the bisulfite ion. We've got dinitrogen monoxide, and we've got the ammonium ion. So please try those for me, and then we will go through the answers, or I will show you the answers up on the screen. Okay, so the first one, the bisulfite ion, has a Lewis structure that looks like this. It is a polyatomic ion, so it does need to be in brackets with the charge on the outside. Its shape ends up being tetrahedral. It also ends up being polar. I don't want to draw all over it here because I'm going to put the formal charge on here. But turns out that this end of the molecule here is nonpolar, so there's no arrows. But the arrows are going out towards the oxygens in these polar covalent bonds. So overall, the electrons are moving towards the oxygens at the bottom of the molecule. So it is polar overall. As far as formal charges go, you should have found a 0 on this hydrogen. You should have a +2 on this sulfur and a -1 on each oxygen. So each one of those oxygens has 6 in the lone pairs and then an additional 1 from the bond, so that's 7 compared to their normal 6. And the sulfur has 1 from each bond, that's 4, which is 2 less than what it normally has. This hydrogen just has half the bond, which would be 1, which is what it normally has. For your N2O, your Lewis structure should look like this. Remember, the least electronegative element should go in the middle. That is your nitrogen. So your central atom should be nitrogen. That shouldn't affect either your shape, which is linear, or your polarity, because this bond is nonpolar between the nitrogens, an electronegativity difference of 0, and this bond is a 0.4 difference, so that's also nonpolar. So there's no small arrows to draw, which means there's no big arrows to draw. So this is nonpolar. As far as your formal charge goes, this nitrogen has a formal charge of -1. It has 1, 2, 3, 4 in the lone pairs, plus a 5th and a 6th from the bond. This nitrogen gets 2 from each double bond, so a total of 4. That's 1 short from what it normally has. And this oxygen has 2, 4 from the lone pairs and a 5th and a 6th from the bond, which is a 0. Those formal charges add up to 0, and the molecule is 0, so we're good. Finally, we've got NH4 + 1, the ammonium ion. The structure of your ammonium ion is tetrahedral. So it sort of looks like this. So the shape is tetrahedral. As far as polarity goes, the difference between N and H does fall in the polar range. However, it is going towards the middle of the molecule. So there is no one direction. We can't draw a big arrow in. There's no overall direction within the molecule. So if you were to draw arrows, they'd all be going in this way. And I can't draw one big arrow going in. So this is a nonpolar molecule. As far as formal charges go, and this should be in brackets as well. As far as formal charges go, each of these hydrogens has just 1 electron, so those are all 0. For formal charge, this nitrogen gets 1 from each of the 4 bonds, which is a total of 4. That's a deficiency of 1, so we've got a +1. If you look at all the formal charges, plus 1, 0, 0, 0, 0, you get a charge of plus 1. So that's a little bit of review and a little bit of new stuff. I want you guys to try the assignment, which is drawing Lewis structures, finding the shape, finding the polarity, and identifying the formal charges, and we'll go over that tomorrow. Have a great day.